first webinar of the 6th Joint Training in Atmospheric Composition, jointly organized by the European Center for Medium Range Weather Forecast with the Copernicus Atmosphere Monitoring Service, the European Space Agency, and the European Organization for the Exploitation of Meteorological Satellites, EUMETSAT. My name is Christoph Schröder from the University of Malaga, and I'm your moderator of today's session. Before introducing today's speaker, I just would like to make you aware of the text on housekeeping rules that my colleague Michelle Zeng from Climate Kick has posted in the chat channel. But back to the webinar session. I'm very delighted to introduce you to Federico Fierli, who will talk about principles and methods of remote sensing. Federico is a senior scientist at EUMETSAT with extensive experience in atmospheric composition, meteorology, and climate dynamics, and he has led significant research on pollutant dynamics, tropical convection, and climate change, particularly in the Mediterranean basin, and is deeply involved in user engagement and training initiatives across Europe. Federico, it is a great pleasure having you. The floor is yours.
Okay, thank you, Christoph, thank you, Michelle, and yes, thank you everybody for joining today. And I also would like to welcome you on this first lecture, on this first event of the Joint School. So you will hear more about the Joint School also in next week in Oslo. But I will just take 1 second just to remind you that as Christoph just said, is a joint event that is co-organized by the 3 organizations with the support of the Copernicus European Program, and that this year is also co-hosted by NILU in Norway. And I think this is the 6th edition of the school that we organize constantly now since 2019. But I won't take any additional time. I will start. Basically, my point today, I have 2 points today to bring to you. So first one is, is basically what is pollution and how it is measured by satellite. So what we can obtain by satellite, because this is basically also some ground for the practical phase that you will have next week. So basically, pollution is, we all know this. But one important point is that to mention is the fact that the emissions, so the methods and the intensity that humans make use for production are changing in time, and then the pollution condition can evolve also in the space of few years. This is the example of Pittsburgh in the 40s, where a big effort during and after the war was taken for the war effort, but also for the reconstruction. And another example basically are the plants that were developed in China after the war. And here is an example with the picture of the Grand Chairman Mao Zedong. One event, basically one of the events that historically we consider the first time when pollution was considered a killer, or were considered a very substantial harmful for the human health, was the killer fog in London of December 1952. And this is a pollution that is related to aerosol, so to particulate. And in that case, in the case of this event, a persistent high pressure area was located in the region of South England, blocking basically both the particles, the soot particles that were produced, but also the production of what we call now secondary organic aerosol that are basically originating from sulfates, from organic carbon, and from the carbon, with a very long period of stagnation. And the estimates were of more than 10,000 excess deaths. In the 70s, so we go ahead in time. The concept of photochemical pollution was basically discovered and formulated. This is an example of Los Angeles. That Los Angeles is also considered one of the I mean, was a cornerstone, was an example in the generation of chemical pollution due to the background conditions. So basically, you will see now, basically, the point is the emission of a precursor, in that case, nitrogen oxides, but also volatile organic compounds that can also come from combustion, but also from natural sources. And then through UV radiation, so through the powerful photons, it is possible to generate ozone pollution, but also particulate matter through the nucleation processes. And you don't see the ozone, but in that case, in Los Angeles, you see this fog that is a so-called photochemical fog that is due to the nucleation from the particulate matter. We have mentioned the volatile organic compounds. That is an important element also in the pollution that goes beyond the presence of nitrogen oxides. So basically, the volatile organic compounds are organic, so they come from the different groups, so from the methanes, the xylenes, the propanes, the butanes, and the origin is both from combustion, but it also, for instance, from agriculture. That is methane. This is just an element to show you that basically the health risk that is related to the long range transboundary ozone pollution here is basically still very important in Europe, and that is the report of 2008. This slide is a sort of small recap of the pollution condition. The take-home message here is relatively simple. So basically, the production of ozone is related to the amount and the efficiency of oxidation of the atmosphere, the amount in nitrogen oxides. Nitrogen oxides are important because are a precursor, are generated by combustion, but are also measured by satellites, as you will see. And basically, we distinguish between two different regimes in terms of photochemical pollution. So the first one is when there are a lot of nitrogen oxides. So it's basically a nitrogen oxide saturated regime. And the second one is a nitrogen oxide limited regime. So basically with the two opposite behaviors in terms of ozone production. So in general, in the saturated regime, what happens is that instead of producing ozone, so instead of reducing ozone with decrease in NOx, there is a production of ozone that goes more through the volatile organic compounds channel, and in some way the OH, the hydroxyl OH increases with the nitrogen oxide decreasing. While in the NOx limited regimes, basically what happens is that both ozone and both the OH terms increases with increases in NOx and in decreasing volatile organic compounds. But I mean, basically here the message is that the concentration of ozone is controlled by the concentration of NO2 and by the concentration of volatile organic compounds, with the different cyclings and also with the balance and the degeneration of the radical OH. I think I can probably skip this and I go directly to the question of tropospheric ozone. So tropospheric ozone increased in the 20th century. These are observations in European mountain sites. So you see here is from Pic du Midi to Arosa to Hohenpeisenberg. So in order to build up a coherent time series, but we see that we have basically a very strong trend about 2.5% per year until the 90s. This is the effect of the nitrogen oxide emissions and volatile organic compound emissions that bring to a trend that is strong, has an exponential behavior, and basically leads to 6 times more concentrations. Another element is on the air pollution are the particulate matter. Basically here we see on the left you see the directives, so basically the pollutant. under scrutiny. So PM are the particulate matter, so 2.5 and 10, ozone, nitrogen dioxide, and these are basically the air quality directive target value. And one important point is that the new WHO, so the World Health Organization guidelines, are more stringent with respect to the current air quality directive. One important information for you is that now the Commission is heading to embracing the new WHO guidelines. So basically halving some of the limits, like for instance for the PM, so the PM 2.5 and the PM 10 on overall they should be halved. While, for instance, ozone should be reduced by at least 20%. So these are even more stringent with respect to now. And where are now mainly, I mean, the big problems, the big stories for particulate matter here are in this moment the most polluted regions. So this is in terms of particulate of PM 2.5 here. This is PM 10. So basically it's more the Eastern Europe and the Po Valley that are affected, while for the photochemical pollution, for the nitrogen oxides, we have basically the most industrialized and populated areas here. So from the UK, and this is the blue banana area, so Germany, France, and north of Italy. While for the ozone, for sure, there is a very important component of the intensity of the photochemical of the photochemical pollution, and then of the intensity of UV radiation. So it's more concentrated in the southern basins of the Mediterranean. One important element is that the protocols, and that is what happens in Europe, so it's from the European Environmental Agency, basically the emission decreased since the 90s. So the protocols that are implemented to reduce pollution are working. Partly, but are working. So basically, we are facing a reduction of emission, at least in Europe. Important here, we don't talk about the ship emissions that are not for the moment taken into account. So the SOx, so the nitrogen oxides here, the sulfur oxides are basically due to the industrial production and not to the emission of the ships. That is another chapter that we will not discuss. Okay. Basically, the message here is, okay, we have a quite complicated picture, but the needs that we have is to monitor the increase of pollution and also to monitor the impact of the protocols that are implemented in many world countries and world regions to limit the effect of pollution. What satellite can do for this? This is the object of the remaining long part of this presentation. Satellite, the advantage of satellite is that they measure at distance. They use techniques of remote sensing, so they cannot sample the atmosphere, because they are from 100 to 1,000 of kilometers far away from the ground, and basically they take pictures. So this is from everything where everything has started. So this is the origin of the Earth images. This is an image from a rocket in 1946. So we started to observe the Earth from outside, and already here you can start to see clouds. But okay, things have evolved. And in this moment, we can say that we are, in the golden age of the Earth observation. So basically in the 90s, there were around 10 Earth observation satellites, while in 2020, we will have about 150 Earth observation satellites. So we can have information on the surface properties, on the wildfire. This is an example on wildfire, on the vegetation, on air pollution, and so on. And then Europe will be in a unique position. Having the operational missions that you will hear about next week, the Sentinels, and the Earth Explorer missions that are implemented by ESA. But let's go now a little bit on what can be observed by satellites. So this is an example. Nitrogen dioxide, you have probably heard about the measurements from Sentinel-5P. We go a little bit back in time. So this is OMI. This is ozone monitoring instrument, so it's the precursor of TROPOMI, that is basically Sentinel-FP. And here we have the possibility to see what happened between 2005 and 2010. So in blue, we see that the columns, the tropospheric columns of nitrogen dioxide decreased, mainly in Europe and the US, while increased in, let's say, most of the populated area, including China. What is quite interesting is that the Chinese NOx emissions, in fact, after 2010, they started to decrease. This is due to basically to the benefit or to the activity that started for the Beijing Olympics in 2010, and the emission basically are starting to slightly decrease. Observing nitrogen dioxide, we can also see different things. So basically, we can see the effect of the changes in industrial production, and this is an example. I mean, it's not COVID. It's not the effect of COVID. It's a paper that dates back of 2012 that tracked the Greek economic crisis in 2011. Basically with reduction of nitrogen oxides here. So we see that we have a decrease during the year due basically to the decrease in oil consumption. And these are the observation of nitrogen dioxide from Schiamacchi. The same here for SO2. And here also we see in Athens, for instance, still with OMI, that is in blue, a drop from 2009 in terms of the peak of nitrogen dioxide. This is related to the decrease of the traffic that is related to the increase of the price of the fuel. This comes from a Nature paper and shows basically a weekly weekly average cycle that can be derived from satellite datasets in different countries. In Europe, so in Europe we see that typically we have a drop in nitrogen dioxide with different regimes. So basically the stronger drop during the weekend is recorded in Great Britain, probably because everything is shut down. Thank you God it's Friday. While is to a less extent in Turkey. While, for instance, in the Middle East, the strongest drop is during Friday. That is okay. The feast day for Muslim religion, while in Israel is for Shabbat. Again, for Asia, the decrease during the weekend is less marked, except Japan, for the emission of all the pollutants. Basically, this is a good way to have an estimate of the impact of emissions on the tropospheric column of nitrogen dioxide. One big point, basically, is I go back to the ozone, and one of the points of the ozone, of the tropospheric ozone, is that despite the decrease in nitrogen oxide emissions, in fact, the concentration of ozone is not really decreasing. So you remember, no, in one of the first slides, we had these trends since the last 2 centuries, or the whole last century. And here again, the data set from Jungfraujoch and Zugspitze, they show a decrease of the intensity of the trend, but they don't show a reverse of the ozone concentration. And in fact, if we make use of the satellite data, and here is again a trend in ozone, what we do observe is basically an increase or a high concentration of ozone basically everywhere in the northern hemisphere, plus a big amount of ozone here in subequatorial Africa that is related to the intense biomass burning. But yes, basically we see high concentration of ozone where you have precursor, and in that case you have a joint effect also of carbon oxide and volatile organic compounds. Here is the trend below, that is again estimated by satellite. This is from the TOR, Total Tropospheric Ozone Assessment Report, and we do observe that is basically a positive trend everywhere, especially in the tropical regions. This is what looks like a trend from satellite. So this is again from the TOR, and here you see how the different instruments, they do observe the trends in the northern hemisphere. I mean, there are shifts, there is a strong annual cycle, but basically all the trends from the satellite dataset are significant from 96 to 2017. In the southern hemisphere is less marked, less variable, but also there are for some instruments, like for instance GOME, there is also a positive trend that is significant. I will probably skip this. I go to another example, that is ammonia. Ammonia is a very, very volatile and fast reacting compound. And again, looking at the difference in 7 years, it is possible to observe, as we have observed for the ozone and as we have observed for the nitrogen dioxide, the changes in the pollution, in the burden of the species that is related to changes in the emissions. And what we see here, for instance, in ammonia, this is the example of Africa, that in West Africa there is a strong increase of the concentration of ammonia. This is related to an increased and more efficient agricultural production. So we know that in the last decade there has been an increase in the greening and in the capability of production and cattle, and that this is reflected by the production of ammonia. That is let's say at the end an emission that is related to the intensity of production of nitrogen. So it's a leftover from nitrogen. On the other hand, is not always like this. So for instance, in South Sudan, there is a decrease. The decrease is possibly related to, in fact, to reduction in agricultural production there, but also in a change in burned area, so in the activity of fires. Still going on the emission estimate, one big thing that is coming with satellite data is about the emissions of carbon dioxide. So carbon dioxide is a big thing, is a big let's say, is a big elephant in the room. Paris Agreement requires to monitor this and to monitor the changes, and then there is a strong effort that you will also hear about next week about monitoring this from satellite. No? So the CO2 existing satellites and the future CO2 monitoring service that is implemented at European level. And basically here it shows how you can identify CO2 sources from satellite with the satellite SWOT, and for instance having increases like this, and using the shape basically of the concentration of CO2, there is a way, there are methods to estimate in some way the intensity of the source that led to this CO2 concentration. One of the difficulties that in fact the CO2 here, I mean here is a bit small, but basically you see that there are changes of a few units, okay, in terms of ppm. So basically you need to have the sensitivity that is going from 405 to 410 ppms. So you need a sensitivity that is more or less, let's say, more than 1%. So you need 0.5, 0.3% of accuracy here in order to be able to see this. Then one of the methods that is used is, for instance, to use nitrogen dioxide. So nitrogen dioxide is observed, is a more binary value. So you have the emission, you don't have it because it's a fast reacting. We will come back to this concept in a few slides. And in some way is used as a trigger. So I can observe nitrogen dioxide, and then nitrogen dioxide is a place where I can have likely also a CO2 plume. For sure, there are also methods of using AI, ML algorithm and so on, but I won't enter in this detail. I mean, it's just for you to be aware of this let's say, of this series of applications. I go now a little bit on some technique, observational technique. So basically, what a satellite observes. Okay. Here below, I made a schema of the different chemical reactions, different processes that happens for chemistry and aerosol in the atmosphere. So here are the aerosol. So you have organic emissions, you have water vapor, you have emissions from in the industry. I mean, I didn't include the natural ones that are also very important, like dust, or wildfire. But I mean, basically the message is that you have emissions and then you have transformation processes. The same for the chemistry. The chemistry, so you have emissions that are anthropogenic, natural, and you have physical and chemical transformation processes. So chemical are all the reactions that we have also detailed before. So for instance, the regime of photochemical pollution that is again represented here. But then you also have dynamic, like deposition, like mixing, like dry deposition, wet deposition, but also, for instance, exchange with the stratosphere. So basically, you have a range of processes that transform what is emitted to a more steady status of the concentrations that then are observed by satellites, because at the end, the satellite observe the the attenuation or the interaction of radiation with matter, so with the molecules, in the whole atmosphere or in different atmospheric layers. So basically, what the satellite observes is a perturbation to a black body emission. No? So if, for instance, we take a reference black body emission here at the soil temperature, at the ground temperature average, climate average, so 20 degrees Celsius, basically this is what a satellite observes. So with all this attenuation of the signal that is due to the absorption that happens in the atmosphere due to the different species. And looking at different spectral windows, you have the capability to estimate the amount of attenuation. And the amount of attenuation is given by two factors. The first one is the efficiency, the quantum efficiency of absorption. But this is known. Okay, this is tabulated, that this depends on the wavelength that we know, that we control, because I mean we observe at a certain wavelength, but also depends on the chemical structure, and this is given. This is atomic. The second part is the amount. So basically, once I am able to measure the amount of attenuation, I have an indirect estimate of the total amount of the molecule. Okay, I will not much enter into this, but I mean, basically the message is, okay, we measure column, so we measure an integrated effect, and I have the possibility to distinguish on different species. So basically, the satellite, they measure in the case of, for instance, in the case of UVVs, or infrared, they measure the interaction of this radiation, sun radiation, with the atmosphere in terms of both reflection. So, for instance, if I go in the ultraviolet, I observe the reflection of the sun on the surface, and then the interaction with the atmosphere. So there is a question of estimating this vertical column, but basically the interaction happens on a slant column, so on something that is oblique with respect to the total column. Then you also have satellites, instruments that work in the infrared, and the infrared basically is directly the emission from the ground, and the emission from the ground in the infrared domain is also attenuated by the atmosphere, but also interacts a lot with water vapor, temperature, and so on. So it's a bit more complicated. Just to mention that, okay, so these are the so-called nadir techniques. So basically, I have a column. That's it. There are also techniques. This is the example of limb scanning. So basically, to have the possibility to estimate the concentration in layers, so to have vertical profiling. And this is due to the fact that the satellite during the orbit has the possibility to make vertical scans. So basically, observing a sort of, let's say, horizontal layers, but that are centered at different heights. And then with the convolution methods, I mean, the most known is the Rogers, but I mean, there are several of them. Basically, it is possible to obtain the average concentration on layers that in general, they have a thickness of a few kilometers. I mentioned it before, the question of the spectral resolution. So here you see a little bit an example of what the past and current satellite they do in terms of spectral monitoring. So basically, this is GOME that is on board the METOP satellites, and you will also see next week. So basically, GOME works here in the UV visible, so in the range from 300 to 700 nanometer wavelengths. Schiamaki, that was on board on EUMETSAT, for instance, has had a quite larger spectral domain, while, for instance, Tropomi has also here an infrared channel, but also, I mean, is a UV visible. So basically, with the TIS and the YASI that I will also mention, works here more in the infrared. So basically, we will have a combination of instruments that measure at different wavelengths, measuring different species. But we will also have the problem and the advantage to measure the same species from different instruments. Okay. I will give here a little bit, a sort of a quick review of the different instruments that are there. So GOM2 is active since 2007 with the different let's say with different sons and nephews. So now we have the third one that is on the METOP-C. And GOM2 is a good example for UVVs, what I mentioned before. So as I said, so basically what happens is that in the UV visible, you have the solar radiation that is reflected, the different layers in the atmosphere. What we want basically is the scattering on the atmospheric ground. So what we need basically is to know how much radiation arrives at the ground, how much is the albedo, and then this is basically the source at the ground. So basically the algorithm of GOM2 makes use of the direct radiation, so you have I0, and then you want to see how much this reflected I0 times albedo is then absorbed by the atmosphere in different wavelengths. And here you see what happens between 225 nanometers to 800, and this is the region of the GOM2 transmittance. So what you see is that you can measure, for instance, ozone here. You can measure formaldehyde, you can measure bromine oxide and the chlorine dimer. Nitrogen dioxide, also here you can measure ozone in the Chapuis band, and you have several points where you have water vapor. So basically, okay, these are all the species that, as you see here, can be obtained. Also, you see here, for instance, water vapor is typically absorbed, so you have a drop in the transmittance. Observation are limited by the cloudiness, because I mean you have interaction of radiation with the clouds. So basically the point is that, especially in the visible, the radiation don't cross. The main point again I need to stress again is the fact that we observe what happens in this layer. So it's not ground. So it's not what happens at the nose level. Same principle for Tropomi, and again here is what Tropomi can observe at the different wavelengths. So from the UV down to the shortwave infrared. Shortwave infrared, greenhouse gases, very important. So we have methane observation. You will see also a lot of methane stories from our colleagues of European Space Agency. Offshore, these are infrared because I mean they are greenhouse gas and then interact with the infrared radiation that is emitted. Since we are in the infrared, the YASI. YASI is an instrument that is also on board METOP, that is an operational satellite, and works in the infrared. Here, now the wavelength are in centimeter -1, but okay, we are in the infrared domain. And then here you see that you can observe nitrogen stuff, so ammonia here. You can observe nitric acid, you can observe ozone, you observe nitrous oxide, methane again, water vapor, CO, and also there are lines that are dependent on CO2 and temperature. Additional 33 species that interact with infrared radiation, so a lot of greenhouse gases can be observed. I mean, looking at the let's say, the changes in these spectral lines, because the advantage of EASI is that it has a very, very fine spectral resolution. Why we want a fine spectral resolution? Because in fact, EASI was built up not necessarily to measure the chemicals, I mean, for sure, it's one of the primary objectives, but also to have an estimate of temperature. So basically, the point was to be able to observe the emissivity of at a different temperature, at different wavelengths, because as we know, the temperature changes with the height in the atmosphere, and then in some way, every layer is representative of a different emissivity temperature. And then in some way, this was, the objective of EASI was to observe the changes in emissivity at different heights. So the possibility basically to reconstruct or to have information on the radiance, on the infrared emissions at different heights, and then is crucial for meteorology, basically for meteorological assimilation. Of course, with weighting functions. So the layers that we are considering are not necessarily one ideal layer of zero width, but in general, they are representative of a thinner part of the atmosphere. And here are the so-called weighting function. So basically, how much the single layer is representative and which part of the atmosphere it embraces. We see that the lower weighting functions that are the more interesting for us for the part of the pollution, as you see here, basically they are representative of a good bunch of the troposphere. Orbits. So we have discussed about the spectral resolution. Now we go to the orbit question. The orbit question is important because basically it determines what is measurable, what is the resolution, and what is the time coverage. So basically we have two type of orbits. The first one is a sun-synchronous, is a polar, you see here in the picture. So basically you have a satellite that always observe at the same time, the same point of the Earth. So basically it's there and the Earth turns below, or vice versa. But basically the message is that the satellite makes what? So basically observe on these belts. The satellite in this orbit for geodesical and orbit reasons is in an altitude that is between 300 and 600 kilometers height, like the International Space Station, and then is relatively close to the ground, relatively close to the surface. So you have the advantage of having more signal. So you can have a higher spatial resolution, you are closer to Earth, and you can also use active observation like radar, LiDAR, and so on. The problem is that you don't have a constant coverage in time. So basically you reobserve the same place after one day, few days, but you also observe it at the same time. That is a limitation, especially for what is fastly evolving, like, for instance, nitrogen dioxide that has a very clear daily cycle. Geostationary observe always the same phase, so basically it orbits together with the Earth. The advantage is that you always observe the same phase, so this is EUMETSAT. So basically, so you always observe the same phase, so you have the time resolution, you see a movie. But the disadvantage is that on one side you observe just one side of the Earth, and then you need the constellation, but we have them, we are building them. The point is that you have larger viewing angles on the borders, so you have a sort of distortion, and also you are far away. So embark there, active remote sensing is no way. And you need very sensitive devices, very sensitive observing systems, because basically you are at a higher distance. What you can observe, from polar orbit, as I said, you have this type of belts. So for instance, this is visible together with firepower, so with detection of fire pixels. This is an example that comes from firms from NASA, and also, to be fair, here are our colleagues from ESA, and that this is Sentinel-FFP, the measurement of CO. So what happens here is that even if this looks like a map, so basically every SWOT here is observed at a different time. So in the case of CO that is okay, evolving, but has a quite long lifetime, basically, I mean, this can be assimilated to a map. But in case of a fast evolving species, I mean, we need to take this information with more care. Geostationary, I mentioned the Meteosat that you probably know, but I want just to give you a very short overview, very short, about the fact that we have a Meteosat third generation sounder is implemented by EUMETSAT with the support of Copernicus program together with the European Space Agency, and for the benefit of the users, and the primary users is ECMWF. So it's always the organizations that organize the school that are involved there. And basically there will be two instruments that will observe in geostationary ways. So the first one is an hyperspectral infrared sounder, so it's a big YASI. And the second one is a Sentinel-4, so is UVVs near infrared. So is a Sentinel-5P. And as a Sentinel-5P, can observe in that case nitrogen dioxide. This is a simulation of what Sentinel-4 will observe with a time resolution of 1 hour and with an horizontal resolution of about 4 to 6 kilometers. And this is an example of the production of nitrogen dioxide from wildfires during the summer 2021 in Greece and here in South Italy, with other points here that are basically the nitrogen dioxide emissions that are nitrogen dioxide concentration that are due to the emissions of the town of Naples and the town here of Bucharest. Just to give you an idea, a geostationary satellite comes with a high intrinsic, quite high resolution. This is an example of GEMS, that is the Korean UVVs spectrometer, geostationary. That is already flying since 3 years. And here is compared to what we have with the GOM2. So GOM2, these are both observation of nitrogen dioxide. And you see that basically the two satellites, they are able to observe and to identify the regions, but this is at one fixed time. This is an average over different times, so you can monitor the evolution, and of course, sure, there is a question of increasing the resolution. This is part of the constellation. So mentioned Sentinel-4, mentioned GEMS, and the TEMPO has to be mentioned as well. TEMPO is now flying. The first test data are getting out, and so we are really hoping, in a relatively short time, to have, these three, okay, observing spot points. I need to move a little bit on going a little bit more in detail on what is observable, what is observed, and which is the role of the atmospheric lifetime. Because we have said, okay, we have stated, we have seen that we observe a vertical column. So basically we observe an average concentration, okay, a steady concentration. And what determines a steady concentration? So basically if we have a concentration C here, okay, the concentration C, or the variability in the concentration, is due to two factors. So one is the wind, so is the circulation, and here is the divergence, okay, is the scalar product between the U, that are the atmospheric winds, times the gradient of the concentration, plus production terms and loss term. Basically, what does it mean? It means that production is typically what is emitted, but also what is generated in the chemical reaction, and loss is what is deposited for instance, on the land, on the oceans, but also what is lost in the chemical transformations. So basically, what you need is to estimate the circulation, but also the intensity of the loss and production. If we close ourselves in a box, so we imagine that with the satellite we are observing a box. So we observe what happens there in the box of atmosphere, and I want to know what determines the concentration that I am observing. So I have the emission that at the end is the thing that I would like to estimate if possible. But the concentration X is given by what enters here in the box, what goes out from the box, what is produced locally, what is lost locally, and what is lost in terms of the position towards the ground. And then I can estimate an atmospheric lifetime. So basically, atmospheric lifetime is the total amount of the pollutant or of the species M. Beware, this can be aerosol, can be water vapor, can be CO2, can be whatever, and is the ratio between this mass and what is removed, so the mechanism of removal. So basically, this is okay, this is the result of the differential equation, and basically is total mass ratio outflow, so what is transported out, what is lost in terms of chemical, and what is lost in terms of deposition. We need to define, to know which are the typical lifetimes, okay, of the species. Okay, the atmospheric, this is the lifetime that is due to the different, basically to the different chemical and dynamical processes, okay? The atmospheric lifetime, so the chemical lifetime, so what happens here, so in terms of this term L and D, so is in some way the reactivity of the species can be very long. So for instance, for CO2, CO2 and O2, sorry, N2O and CH4, this is N2O, is a nitrous oxide, is about ranging from 10 to 100 years. So we know that these are long-lived species, while the pollutants like NO2 is of the order of days, carbon monoxide is of the order of weeks, formaldehyde and so on are of the order of hours to days, and ammonia is of the order of hours. So these terms that are here, so is the loss, we need to understand if the loss is stronger than the circulation. So basically, what is dominant? Is dominant, let's say, in determining the lifetime, so how much time the species stays in the box. If it is dominant, the question of chemical or the chemical reactivity, or if it is dominant, the question of the circulation. The typical scales for circulation are in the free troposphere are a few weeks in order to make the tour of the Earth, 1 month to cross, for instance, up and down from the mid-latitudes to the tropics, and 1 year to have an interhemispheric exchange. There is also a question of the vertical exchange, because the emission happens at the ground. So basically what happens is that until the first couple of kilometers, the process is the dynamics of the PBL, that the planet boundary layer that I have tried to exemplify here. So basically with the formation of a mixed layers, but mainly the message is that typically the lifetime, so the transport time is about 1 day. So we need to have a full cycle of the boundary layer in order to mix up and down the emission that happens at the ground, while in the vertical, going further up, so basically we have transport time in the free atmosphere, in the free troposphere, of about 1 week, and then in order to cross the tropopause, so to enter in the stratosphere, is a question of years. So again, you have 3 regimes: 1 regime fast, that is of the order of the day; 1 regime that is average, that is order of the month, that means global in the troposphere; and then a 3rd regime that is totally global, so interhemispheric plus stratosphere, that is of the order of the years. And in fact, what we see here is that you have a temporal scale, but also a spatial scale of mixing. No, so basically, the shorter lived are the species, the smaller is the spatial scale. So basically, for instance, nitrogen oxides, they will have a scale that is of the order of the kilometers in height and in distance. So basically, these species, they stay quite close to the emission. While for the carbon monoxide is more difficult, because you have carbon monoxide that is transported, because it has a lifetime of a few weeks. So it can, for instance, be transported over the globe, while for the greenhouse gases, they are so-called well mixed, because in some way you lose quite track of the emissive point. Remember about the question of carbon dioxide. And also the vertical profile here. You see, this is the example of the mixing ratio versus height. It tells that the shorter is the lifetime of the species, the more concentrated will be the species close to the ground. So the more sharp will be the profile. So 0 here and very high here. While the longer is the chemical lifetime, the more efficient will be the vertical mixing. And then you will go for species that have 100 years of lifetime, like carbon dioxide, you will have a sort of a flat vertical profile. So the species is well mixed also in the vertical. Then let's see the effect of this. Here we have nitrogen dioxide. This is from Propomin. This is 1 month accumulated. But as we see, with nitrogen dioxide, we are able to identify emissive spots. So because the lifetime of carbon dioxide, as we said, is of the order of a day. So basically, it stays close to the emissive regions. But beware, this is still the tropospheric concentration. Ammonia has a lifetime of hours, so is even closer to the emissive region, and has the difficulty that since it reacts very fast, basically the concentration are very low. Why? Because if you go back to this equation, basically these terms are big. Okay, these terms is small, and then M becomes quite small. So basically the remnant in the atmosphere is quite small. So here we are also really talking about PPBV, so pico parts per volume. So we really need to have a very, very, very good accuracy, or to work with a strong accumulation of data. So this is, for instance, how it looks like, the measurement from YASI. So you have points, and then you need to average over different time scales, really, in order to accumulate or to sample. This is the example of hotspots that have been identified, but this is a 8 years accumulation of data, with the possibility to identify really, single hotspots of ammonia emissions. And these are, for instance, single plants of fertilizers and so on. So I remind you to these papers from Lieven, Clarisse, to see this. If you go to CO, I have 2 minutes more.
Yeah, exactly. I just wanted to ask you to start.
Okay, perfect. Yeah. I'm quite close to the end. Nitrogen monoxide, carbon monoxide, as you see here, is quite well distributed. So you see the concentration in the northern hemisphere. A lot here in the Southeast Asia, where there is a strong emission. Here are the fires again, pollution in Mexico, and much more in the northern hemisphere with respect to the southern, because it takes 1 year to cross the equator, and then basically the emission from north hemisphere, they do not have the time basically to reach the southern, because the CO is transformed before. Just 1 point about CO. Here you see that you have also an annual cycle that is quite intense, and is really depending on the emissions, on the burden of emissions. And in that case, what really jumped to the eye is the intensity of the changes of the intensity of emission due to the wildfires. We said, okay, CO doesn't stay in the atmosphere, while CO2, that is oxidized CO, has a much longer lifetime. This is 2010. So don't jubilate, don't be too happy, because the concentration now is 410 to 415. So this is a previous in the previous decade. But what you see here, for instance, is that you see differences of about 10. It is micromole per mole, so but it's about 10 ppb, 10 ppm. Sorry, 10 ppm. That is due to the fact that you have a difference in transportation from the northern to the southern hemisphere, as we said before. So basically, you see in the southern hemisphere the CO2 concentration of a couple of years before. So you see the effect of the emissions that were happening a couple of years before. Last word about the aerosol. I will not have the time, but I mean I will leave you the presentation here. I just want to mention in 2 minutes the question of wildfires, because the wildfire will be object of the practical part that is that you will find next Monday. So basically, wildfire is a big thing. Is changing. Is a natural source, but is also much impacted by the climate change. Climate change is changing the current and will change the future fire regime. An example is from Arctic. We will have a prolonged fire seasons. But we also have a strong need in satellite observation. The example is, for instance, on the burnt area that you see here. And the burnt area shows that there is, for instance, a decrease in biomass burning areas in Africa. But again, I mean, the uncertainty is still there. And this is an example, for instance, on how the Canadian wildfire reached Europe. This with long-range transports. And this is an example of what happened with the Australia bushfire. So that reached 35 kilometers of altitude with layers of smoke observable with calliope. What you will see, and will be introduced by Dominica, is the measurement of smoke, but also the measurements of fire radiative power. So basically, is an estimate in the infrared of the intensity of the fire that has a very clear infrared signal, and is observed as difference between channels, and gives the possibility to identify the position of fires like this and relate them to the smoke. So I will stop here with the lesson learned that we have. So we have a very large amount of satellite observation, and this is increasing. I will try to be very synthetic. Many geophysical variables that are essential for atmospheric composition, pollution. We can use them for supported emission estimate. However, important, we need the schools like this one, because are not always easy to interpret. And there are many issues in terms of, or points that you need to know and you need to work on in terms of coverage, representativeness, and also uncertainty. So I stop here. I've been just a bit long, but
yeah. Anyway, thank you very much, Federico. It was really a very comprehensive overview of the state of the art, and I think a very good introduction also for the webinars that are upcoming on modeling, forecasting, on data assimilation, evaluation, validation, and the downstream services. So now we have, I think, the basics for the upcoming webinars and also for next week's on-site course. I don't see any questions so far. I wonder whether the participants have any. They can, as mentioned before, write them in the question and answer part. For the time being, maybe I would like to, as a first icebreaker question, a bit now based on also what you mentioned, ask about with forward looking. So in your opinion, what are the most pressing issues and upcoming challenges in remote sensing in the context of atmospheric composition, taking into account also a bit this triangle of spectral, spatial resolution, orbit, where is there still a lack, where should it go, and where is it going in terms of European and global observation?
I try to cut the question in two.
Okay.
So the first one is, okay, we have observations. So we have and we will have more and more. I haven't mentioned also the private initiatives. I mean, we have EUMETSAT. I mean, we really expect in the space economy to have an increase of the monitoring. So the first thing is to make a synergistic use of them. So to put them together, or to understand what you can have from one technique and what you can have for another technique. I mean, one example that I haven't discussed now, for instance, if you measure atmospheric dust, and you can have atmospheric dust from the infrared, but also from the visible, you have two different measurements that have two different sensitivities, two different errors, and they try to measure the same thing. We try to have an information on the same thing, but you have differences. So it's really, let's say, from the scientific and technical point of view, not easy. The second point is about what we need to measure. So basically, okay, the big thing will be to measure well the CO2, the carbon dioxide, and the different species. And what will be important is also to be able, in terms of research, in terms of science, to make use of the satellite for the processes where we have more unknown issues. So like, for instance, I've mentioned the secondary organic aerosol, but I mean, they're not even secondary, because in many regimes, they are the primary source of particulate matter, no? So, I mean, also having the possibility to measure the species that are behind this, and also to relate that to the level of particulate matter. So for this, you really need to go more and more down and to have more and more sensitivity and the capability in observing, let's say, thinner layer or lower concentration. Then there is a question of resolution. So basically, many of the applications really require to go at, let's say, plant level, or to go at single emission point level. So we really have many requests to go for applications that also consider climate change at very local level and the impacts. So this is another aspect. So basically the resolution. And then there is also an element that is close to my heart, because I was working on stratospheric ozone, is that we are losing the capability to monitor the layers. So we will not have very, very soon the capability to monitor the vertical structure, the vertical distribution of, for instance, carbon monoxide, ozone, and so on, because microwave beam sounder that is on the very successful Terra Aqua A-Train system will be shut down. I mean, we really need to give continuity, no? Because it's important also in terms of climate datasets, but also, I mean, to understand things or to discover things that were not seen before. For instance, with the instruments, with the instrument MIPAS that is able to measure ammonia, no, at 15 kilometers, was able to identify the presence of ammonia at 14 kilometers height as an outflow of convection above polluted regions. I mean, it's important because it really contributes to the progress of science.
Very wonderful. Thank you very much. There are a few questions, and so starting with Bertrand, if you like to, you can open your mic if you want, and pose your question.
It's up to you. It's I mean, I can answer. I mean, desert dust.
Yeah. Okay. Yeah, exactly. Yeah. I just summarized for those who maybe not see it, particularly also in the streaming. So there's a question on, would you like to say a few words on desert dust and how their concentration are measured and the variation?
I mean, if I can take just 1 second, here is it. I think it's this is faster. Let's see if I have this. Okay. This is basically how it is possible to observe dust. I don't know if you see my slides, but it is how dust can be observed in the visible. Okay, here is it. Basically, this is an example of dust that is an outflow from Sahara. So it has a different color because there is basically an optical depth. So the aerosol act as a reflector, absorber, but in that case a reflector of the radiation, and in some way is seen as a sort of screen. It screens the reflection from the ground, so it has a different color. What is interesting here is that you see that basically the albedo, so the reflection from the sea, is different, so it's much lower, while the reflectivity of the aerosol is higher, so you see very well the layer of dust if you look in the visible above the ocean. Less easy to see it above the ground, where the level of albedo is very similar. In that sense, for instance, measuring the infrared is interesting because you are more independent from the from the albedo and from the difference of the surfaces. But basically, in general, I mean, at this slide you see how the dust, like most of the aerosol, are observed by satellite. So basically, it's a reflector that enters here and provides a signal here in the measurement of the reflected light from the surface. So this is in a nutshell.
Very wonderful. Just to link it to another question on dust and dust storms, a question by Hamid on the remote sensing tool to observe dust storms, particularly in North Africa.
Yes. I think again here a question of synergy. So in some way, for sure, the satellite is very important because, for instance, in North Africa you have the Meteosat, and you have now also the Meteosat third generation. So you have measurements every, I mean, few minutes, so you can see the evolution of the dust storm. One of the points is also the observability at the ground, but you can use, I don't know if I still have a slide, but I can give you offline every element. So you have the possibility to combine infrared channels in order to have a product that is called the RGB, basically that is sensitive to dust, and then you can see the evolution of the dust plume. Two caveats. First one, okay, is whole atmospheric layer, so you cannot identify the height. And the second caveat is that there is an influence of the clouds, so you cannot easily see in the presence of clouds. However, you also have the possibility to measure in the UV. So there is the so-called aerosol absorbing index in the ultraviolet that is also provided by Tropomi, but also by GOM2, and that is less sensitive to clouds. So it's you can have a coverage, and also you can make use, for instance, of I mean, there are also ground-based observations that can be used, for instance, for climatology. There are not much of them in North Africa, but I mean, there are more of them, for instance, in the Mediterranean basin. There are the Aeronet and these ground-based remote sensing. I hope that I have answered to the question. But I mean, I can provide any type of material on this.
Wonderful. Yeah, the three more questions I see. First by Daniel Helm, if you want to briefly open your
yes,
I could ask.
Yes, sure. There are methods. There are methods, many of them. So, I mean, methods are okay. As I have really fast shown very fast is okay, making use of observation of species that are closer to the ground, like NO2, for instance, observe the, let's say, the shape of the distribution of concentration around an emissive source, and basically estimate what I have defined before, the term of, let's say, of transport, so of diffusion. So basically it's the inversion of, they try to inverse the equation of diffusion in order to obtain the term E that I have shown in my slides. So this is technique one. AI ML, so there are also techniques that do this in many ways. So inverting the emissions, but also, for instance, inferring relations between satellite data sets and air quality stations. So basically making a sort of intelligent interpolation between the two. So having the possibility to infer from the relation that you can find with the IML algorithm of the dependence and the covariability of ground-based stations and satellite, in order basically to have the possibility to estimate, to extrapolate the ground-based concentration with satellite everywhere. You have CAMS. You have methods like CAMS, so that make use of assimilation. So basically, CAMS assimilate the satellite observation into a full, let's say, a state-of-the-art model. And having a state-of-the-art model, basically you force the model, you drive the model in order to have the most reliable concentration, and then you have internally deterministic systems that deterministic equation that bring you also the information on the ground that is also driven and influenced by the concentration that you observe. And also you can have with CAMS a system of inversion. So basically, yes, there are systems. Everyone has, let's say, limitations and advantages. So CAMS, you will hear about that a lot in the next talk.
Great. Yeah, one more question by Julio Castro, who would raised his hand. Maybe you can yeah, open your mic and pose the question. If possible, short with a short answer. Julio? Julio's, okay, Julio, the floor is yours for the question. You need to open your mic. If not, yeah, maybe we can go first then to Abhishek. You also raised your hand. Please ask a question.
Okay. We have a question from Trismono.
Okay. Yeah. So yeah, we take them since it seems. Yeah, we take the question by Trismono. Yeah, I have a question about the weighting function for measuring the ATM trace gases with ERC. Can you explain more?
Yeah. Okay. Basically, the question is, the point is, it is in the infrared. In the infrared, I will try to be very, try to be simple and quick, but do not hesitate to come back to me if everything is not clear. So weighting functions are intrinsically there because imagine that you sample at the different points in the infrared. Okay, so basically the maximum emissivity, okay, depends on the temperature. So if you have a black body, okay, the black body, maximum of the black body, the position in the wavelength depends on the temperature, okay, at which you have the emissions. So basically, if you have emissions from the lower part of the atmosphere, this will be in a region of the infrared that correspond to higher temperatures in the infrared, while emissions from the higher part of the atmosphere corresponds to emissions that are at lower infrared temperatures. And then sampling, because IASI samples at quite high resolution these different regions, basically you see two things. So you see how much is the emissivity corresponding to different regions. And then if you go in a place where you have both dependence from temperature that is always there, but also you have dependence from CO, basically you see how much your, let's say, line is or your black body emissions is reduced to the fact that you have absorption, for instance, of CO or of ammonia, but this happens in different spectral lines that are influenced by the emission at different heights. So basically you have these two information that are tied together in one single observation. Is that helpful? But I mean, I can provide you for sure some references on this.
Yeah, wonderful. Thank you very much.
Okay.
A very last question, so then we also need to close by Mohammed on, so are there any other recent satellite sensors capable of measuring the atmosphere with a relatively high vertical resolution?
Yes, not only recent. I mean, the highest resolution is basically given by instruments that are really able to, I mean, to sample. In that case, with active techniques. So the highest resolution for aerosol is achieved with lidars. Because I mean, basically LiDAR is a radar, and then you can, I mean, based on the sample, you can decide which is your vertical resolution. So Calliope, Calypso, that I have very quickly shown, that can measure the level of backscatter of the atmosphere, in that case of the aerosol, in general with a vertical resolution that varies from 50 to 100 meters. And now also there is AirCare that was launched not much time ago. I think ESA friends will talk about that. And there is also a LiDAR that will work in conjunction with radar. Reaching this resolution with the spectrals, so with the UV, visible, infrared, spectral stuff, is very, 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 very complex. Because I mean, as you have seen, you would really need to go to an infinite spectral resolution in the infrared in order to be sensitive to, let's say, just one small atmospheric layer. This is, I mean, something that can be slowly achieved, but for sure, I mean, you lose a lot in terms of horizontal resolution. But I mean, arriving to 100 meter for the moment only with active.
Wonderful. Thank you very much. Yeah, dear Federico, thank you very much again for your insightful presentation.
Yes, thank you. Thanks to you, and thanks to all the attendees. As I said, I mean, I am there, so you can really drop question at any time, any moment. I'm happy to answer, and I also would like to enjoy the remaining all the presentation, all the webinars, and also the on-site part of the school for those who will attend. Thank you very much for being there, and have a nice lunch break.
Yeah, have a nice lunch break. Many thanks also from my side to the participants for their interest and participation. We continue the series of webinars this afternoon, 3 p.m. Central European Time, with an introduction to modeling and forecasting by Johannes Fleming from ECMWF. So yeah, see you later, and goodbye.